Hi all, this is Mr. Yeager for chemistry. We hopefully just finished up the video about the factors that affect the reaction rate, how quickly a reaction occurs, and now we are looking at how to calculate reaction rate. All right, so we follow something called the reaction law, okay? And essentially, this is an equation that's going to be a mathematical relationship between the rate and the concentration of the reactants. Again, since we're seeing how quickly this reaction moves, we only need to focus on the reactants forming into products. We're seeing how quickly the product is formed in some ways, or again, how much the reactants are used. So that is really the key part. You know, we don't focus so much on the products, it's on the reactants. So there's just a couple terms that go along with this. You're going to see questions saying, what is the rate order of one of the reactants? So rate order is something that you figure out based on how quickly the reactants are changing by and how that affects the rate. All right? This is an exponential factor that the rate changes by based on the concentration of a reactant. Okay? So this is just, excuse me. This is just a whole number, at least the way we're using it in our class, and will pretty much only be 0, 1, or 2. And so those are exponents. So you'll have something raised to the 0 power, which basically means it doesn't affect it because it comes out to 1. Anything raised to the 0 power is 1. All right? Or it can be raised to the 1 power, which basically means if it changes, you know, if you double it, the other side will double it. Okay? So it's basically a 1-to-1 relationship there. If it's squared, that's where if you double your reactant, it should quadruple your rate. All right, and I'll show all this in just a moment with a couple questions. It's basically kind of like a quick data analysis part of it, and if you're really good at kind of seeing the relationships, the proportional change, this is pretty quick. There's a second part to the rate equation. We're going to have a little k value. I know we've been doing all these k values, a capital K with equilibrium. This is little k, lowercase k. And this is called the specific rate constant for this reaction. That can only be manipulated based on the temperature, but we're not going to really do that too much in this class. That's more of an AP Chem type thing. So we have the orders of the reaction, which is the exponents, and then we have k, the specific rate constant. So this leads us with, and I'll rewrite this out so we kind of see it this way, our equation of the reaction rate is equal to k, which is our reaction constant, times the concentration of one particular reactant, which I'm going to raise to some power, that's the order, and then possibly be multiplying it by a second reactant, and then raising that one to some order as well. So these exponents are what we're referring to as the rate order. And then once you actually do with those, if a question says, what is the reaction rate order? This is easy. Okay, you just simply add up the exponents. Okay, so you know if one is 1 and the other one's 2, the reaction order is 3. All right, in what we're saying there, and obviously we're saying that that's the kind of how quickly it can adjust to the changes in the concentration here. So how does this basically all work? How do we use all this? Okay, so here we go, jumping straight to some examples here. Okay, boom, boom, boom. All right, so this is a good question to kind of start with. And I mean, I'm going to tell you basically one of the things here, guys, is, you know, we are given this reaction at the top, but the coefficients don't really mean anything this time. I know that's something kind of weird because we've already been saying the coefficients have been super important since stoichiometry, really. It's not going to matter so much. Really what you're focused on is this data down here, okay? And so these are your 3 general questions that we get. All right? What is the order? What is the reaction constant? And what is right out the rate equation itself? Like that's how we like to kind of go through this. So how does this basically work? Okay? All right. This is what I mean by you kind of just do some very quick data analysis with it. What we want to do is we want to see how the concentration of the first reactant, in this case NO, will affect the rate at the end. Okay? Is what we're looking at here. And then we will then repeat that process using the other reactant, H2. But we want to look at this where we're only changing the concentration of one of the chemicals at a time. So if I look at experiment 1 and experiment 2, the concentration of H2 is not changing. So therefore, between the experiments, H2 is not well, I mean, obviously it affects the rate, but it's not going to be the cause of the change of the rate of reaction, okay? But for NO, it looks like I half the rate. Or not, sorry, I half the concentration. I half the concentration. So I'm going to actually kind of do this the other way. I'm going to look from 2 to 1 because I think that might be easier. So from reaction 2 to reaction experiment 1, I double my concentration. Well, what does that do to my rate? And all I need to do is basically just divide these two. If I do 0.136, and I mean this is something I feel like some of you could kind of like just look at and see, divided by 0.0039, this basically is equal to 4. So what I'm saying here is I am doubling the rate, so I am going 2 times, I keep on saying rate, I'm so sorry. I'm doing 2 times the concentration of NO, and when I double the concentration of NO, I increase the rate 4 times. So what's the relationship there? That means, well, you know, how are 2 and 4 related? I understand you can do 2 times 2, but we're looking at the exponent. So 2 what is 4? The exponent would be 2. So that means the rate order of NO is equal to 2. Okay? And we'll do another one. Again, this is the first one. You might be like, wait, what? And I know I've been kind of saying concentration and rate wrong. But let's go to the next part. Let's look at now, we're focusing just on the order of H2 now. So I want to pick 2 experiments where the NO stays the same. So I'm going to do 2 and 3. Okay? 2 and 3. If I look from 2 to 3, what happens to my concentration of H2? It doubles. Okay? What happens to my rate? Again, I can just divide it. 0.0678, if you can't see it, 0.0339. Guess what? It doubles. So that means these two are directly related. That it means H2 does affect the rate, but only does it basically 1 to 1. So the rate order for H2 is equal to 1. So now you found your 2 rate orders. So check mark number 1. Now it says write the rate equation. So we just write out rate equals K, and then we write brackets NO, and what did we say we're going to raise it to? 2, and then brackets H2, and we can raise it to 1, but we don't need to write 1 as usual. But it does affect the reaction. We are saying that if I change the concentration of H2, it will affect the rate. Again, we got to look at this algebraically. I mean mathematically. I mean either one, whatever you want to say with it. But that's basically it. So that's your rate equation. Now from there, we can now calculate out the rate constant. And all you do is you just pick out any of these experiments. It doesn't matter which one you pick. So let's just pick number 1 because it's right there. And what I do is I go ahead and I have my rate, and I have my 2 concentrations, and I'm solving for K. So if I do 0.136 equals K, NO is 0.420, which I'm going to square, H2, which is 0.122, I don't need to do anything with that, and I solve for K. Basically, I'm dividing all of that stuff to the other side, 0.420 squared and 0.122, and I'm going to put it underneath this on the other side, 0.420 squared, 0.122. And so if I plug all this in, 0.136 divided by 0.42 squared times 0.122, I get a reaction constant of 6.32. Again, that's rounded to 3 sig figs in this case, 6.32. If you want to check any of that, if you want to be like, wait, did I do it right? All you do is now use this same equation up top, put K on in, plug in your concentrations, and see if you come out to essentially that rate. So for example, if I plug in 6.32, I'm going to do experiment 2 now, and I'm solving for rate, which I know what it should be. So I typed in 6.32 times 0.21 squared times 0.122. Oh my gosh, it comes out to 0.0340. Should I start crying? Is that too far away? No, that's basically the same number. Okay? So that's how we can do a rate law problem. So let's try one more. I know I don't really have a lot of space. I'm not going to do that one. Let's just do this one. So I like this one. This is kind of breaking everything on up some. Actually, let's skip that one. Sorry. Oh, I have no more. Let's just look at this one. We'll do this one right here. How about that? This is just x and y. So for this one right here, what I got is, I'm going to solve for the order. So let's see what happens here. I'm going to start with x. What is the order for x? What am I doing to my concentration between 1 and 2? I am doubling it. I don't care about the rest. Like, again, focus just between two trials. And for those two trials, my concentration of y remains the same. Okay? So I basically am multiplying this by 2. I double my concentration. If I do these two numbers, 0.012, 1.2 times 10 to the second, divided by 6 times 10 to the negative third, guess what? That's 2. This is double. So what does that mean about the order? Because it's 1 to 1, maybe that's the way to think about it. The order for chemical X is 1. Okay, for every little bit I increase the rate by the same amount. All right, what about for Y? Well, I need to see where Y changes. So the thing is, all three of the first experiments for Y, it's the same concentration. Okay, so let's go to, this one I want to try to keep X the same. So that means I'm going to use 1 and 4. Because X stays the same for 1 and 4, but Y is doubled. So Y gets doubled here. So if I change the Y, the rate goes from 6 times 10 to the negative third to 6 times 10 to the negative third. So what does that mean about Y? Y has no effect, which means its rate order is 0. It doesn't have any effect on it. So if I increase the concentration of Y, it does not affect the change of the concentration. It must be something, and a lot of times this generally seems to turn out to be like water, where it's there, but it doesn't affect the rate. Okay, it's only the other chemical that's actually trying to do something in it. The water's just kind of sitting there. Okay, so my rate equation would be rate equals K X exponent 1, so I don't write it, and then I don't even write Y. I mean, I could sit there and be like y to the 0, but hopefully you know anything to the 0 power is 1, so we don't even include it. Okay? It's not going to be in our equation. So that leads us then to our final part. Let's solve for k. Again, just pick any random experiment you want. Let's go and just randomly pick number 3. Why not? You could pick number 1. It doesn't matter. And our rate for 3 is 2.40 times 10 to the negative second equals k times x, 4 times 10 to the negative second, and that's it, and I just divide it. So I get k is equal to 0.6, and that is your reaction constant. All right? So again, you're only looking for these relationships. If the rate does not, the concentration does not affect rate, the rate order is 0. If the concentration doubles or triples or quadruples and the rate does the exact same change, that means that you have a rate order of 1. All right? If they change evenly, and then the only other one that's going to kind of come up frequently, it's not something special, okay, would be where if I double the concentration, and what happens over here would be this would become 2.4 times 10 to the negative second. That would mean it increased 4 times, so that means this is a rate order of 2, and that means you are squaring the concentration when you plug it into the equation. So those are the only 3 that came up. I guess the only thing I didn't specifically go back to and explain, let's look at this equation, is if you get the question, what is the rate order for the reaction, for the entire reaction? Like I said, you just add up all the exponents. So since you only have that one, the rate order of this one is 1. If you had, that was 1 and this one was 2, our rate order would be a total of 3, and so forth. But that's pretty much it. Hope you got it. Make sure you practice. Thanks.